second speaker in this morning session is Keshav Aggarwal. He is assistant professor at IIT Bombay, working on subconvexity bounds and related topics. He will talk about applications of the delta method.
Thank you so much. And so we have seen two applications of circle method / delta method so far, Waring's problem and Goldbach's conjecture with that uses the classical circle method. And then we had Stokes, where he spoke about counting rational points on surfaces, where they use DFI delta method. We are going to talk about another application, which is subconvexity bound problems. And we are going to look at yet another delta method, which is somehow a little easier to write and is more flexible. It's not as powerful in a lot of ways, but for our problem, it's going to be sufficient. So let me start with just the Riemann zeta function, right? So let me first tell you what is a subconvexity bound problem. So let's just write our Riemann zeta function, which we know a priori converges for real s bigger than 1, and that we know that you can continue this to the whole complex plane. We know that there's a functional equation. So for example, if you write this completed zeta function, then you know that it satisfies a certain functional equation like this, right? Here, I mean, just for the sake of completeness, because this is a workshop, just to recall that gamma function, this is nothing but the Mellin transform of e to the negative x. And also the fact that this gamma function has some nice explicit asymptotics. So we have the Stirling's approximation. So the Stirling's approximation is that gamma z is square root of 2 pi over z and z over e to the z 1 plus. And this is true for the argument of z in absolute value strictly less than pi. If you, all right, okay. So this is thing, and you can essentially use that in order to find how fast the Riemann zeta function goes. So, for example, well, if the real part is again bigger than 1, you can literally just put the absolute value inside, and you get this is 1 over the absolute n to the s. But we know that the absolute value of n to the s is nothing but n to the sigma. And we know that this converges if sigma is strictly bigger than 1. So the rate of growth as t goes to infinity is nothing. That is, it grows with exponent 0. So let me just call for notation, let's say that A is the infimum, or let's say A sigma is the infimum of all the C's such that you have the growth as the sigma. And of course, we want to somehow stay away from 0. So let me also make sure that t is bigger than 1. Okay. So we are basically seeing how fast it will grow. And because it converges here, we know that A sigma is equal to 0 for sigma, well, strictly bigger than 1 to begin with. And of course, for sigma is equal to 1, we also know that this thing is bounded by, well, we have better estimates now, but it's definitely bounded by log t. I think the first time it was proved was because of Mellin. Mellin proved this in 1900. Of course, just take t bigger than 1. And so, of course, we can say the same thing, that the rate of growth of the zeta function at real s is equal to 1 is also like t to the 0. So if you, sorry. C, of course. I'm sorry. Why should there be a sigma? Thank you. Yes. Thank you. Sorry. And yeah. No, I want how fast this thing grows. So at sigma, I want to see the exponent of t. All right, thanks. Okay. Say again, please. Yeah, yeah. I could not understand. Yeah. Sure, 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 sure. Okay. All right. So I guess certainly we know this, we know something better. Yeah, okay. So let's just make things a little graphical. So let's look at 0, 1. And over here, let's map sigma here. Let's map a sigma. Right? So all we are saying so far is that the rate of growth here is 0. And if you look at the functional equation right here, you can write what is zeta 1 minus s in terms of zeta s. So you can say that zeta 1 minus s is going to be pi to the negative s over 2 gamma s over 2 divided by pi to the negative 1 minus s over 2 gamma 1 minus s over 2 zeta s, right? And that basically tells you, if you use Stirling's approximation over here, you will see that the rate of growth here is going to be that zeta of sigma plus it is less than t to the 1/2 minus sigma. I'm not showing you how the Stirling approximation works, but essentially you have to use Stirling's approximation and do the math, and you will get this. So the point is that if you are interested in seeing what happens between 0 and 1, so this point is 1/2, then you can use the fragmental Lindelof principle or the convexity principle. That is what happens in between is exactly, well, at least determined by the convex combination of these 2 points. Okay, so conjecturally, we have something like this. So in orange, let me write. This is the point. So this thing is the conjecture. And this is the convexity bound. Okay. So if you want to see what happens at the real part equals 1/2, you just take this line, intersect it right here. This is going to be 1/4. Okay. And what you basically get from here is that at the 1/2 line, you have the rate of growth as 1/4, and maybe out of caution, let me throw in any arbitrary epsilon positive. Right. This is known as the convexity bound. This conjecture is the Lindelof hypothesis. And it's a consequence of the Riemann hypothesis, actually. So the Lindelof hypothesis at 1/2 actually tells you that zeta of 1/2 plus it is going to be smaller than t to the 0 plus epsilon. So just this. And subconvexity bound is, so this is Lindelof. This is convexity. And any bound in between is called subconvexity. So something smaller than convexity is the subconvexity bound. So for the Riemann zeta function, for example, you have the bound, something like t to the, okay, I've been writing 1 plus, so 1/4 minus delta for some delta positive is what we would call as a subconvexity bound. So the purpose of my talks is going to be to look at GL2L functions and try to prove a t-aspect subconvexity for those functions, and not just give you the heuristics, but also try to indicate why those heuristics work. And hopefully that will also prepare you a little better for some of the lectures that will come next week, who will be just talking about heuristics, so that you can have in your mind why the heuristics follow. Okay. So far, so good. So you can use similar principles actually, and also get a convexity bound, not just in the t aspect, but also in what's known as a level aspect. So what you can do is you can look at Dirichlet characters of, say, level q, and then you can say that q goes to infinity. And you look at the L function. I guess for simplicity, let me just look at the point 1/2, not at the line. And you can ask, how fast does this thing grow? So again, so the growth as q goes to infinity. And the convexity bound over here is going to be very similar. It's going to be q to the 1/4 plus epsilon. Right? And the subconvexity bound problem over here is again going to be to get an exponent which is smaller than 1/4. And this also follows from the fragment Lindelof principle, but it also follows from the approximate functional equation actually, right? That's what Matt had. So the approximate functional equation is something that Matt had defined for us. And let's look at that and see how this convexity bound actually falls from there. Before that, although, let me define the conductor of the zeta function, or L1/2 chi, where chi is a Dirichlet character. So also recall that the zeta function has an Euler product. So this has an Euler product that looks like this. And notice this thing, this is a degree 1 polynomial in p to the negative s. Okay. Similarly, if you write ls chi for real s bigger than 1, you again get a degree 1 polynomial in p to the negative s. Okay. So we call these as degree 1 L function over Q. And the conductor of so the conductor of this Riemann zeta function is going to be defined as 1 plus t raised to the degree of this L function. In this case, it's 1 plus t. And the conductor of ls chi is going to be the product of the Archimedean and the non-Archimedean parts. So it's going to be the product of the IT part. So if you also let t go to infinity, so you get this, and the Q is capturing the level of your Dirichlet character. Okay. And this basically, so you can basically say that the convexity bound is whatever your L function is bounded by the conductor to the 1/4 plus epsilon. So this is what the convexity bound is going to be. This notion of conductor was defined by Ivanich and Sarnak, and they showed a very general convexity bound out of this, followed by Gerge Hartosh, who showed a uniform convexity bound. And what we are going to do is we are going to assume a certain notions that given the L function, we can write the approximate functional equation as Matt had done it. And after that, we can expand out the L function on the 1/2 line, and we can work with those Dirichlet polynomials. And we are then going to try and get a bound which is going to be like conductor to the 1/4 minus something smaller. Okay, good. So I guess I should also comment that what's known, for example, so the first subconvexity bound was by the method of Weil. Weil did not exactly write it down, but it is by the method of Weil, which is zeta of 1/2 plus IT. That grows like t to the, well, 1/6 log t. And this has been improved several times. The best known is now because of Gauguin. So the record so far is by Gauguin. And for L1/2 chi, the first thing was by Burgess, which is q to the 3/16th. It's less than 4/16th, which is 1/4. This is referred to as Burgess type bound. And the best known is now a Weil type bound. So it is also the same power, q to the 1/6th, and that's a recent breakthrough by Petrov and Young. This builds on the breakthrough of Conry and Ivanich, and they're able to get the bound of q to the 1/6th, right? So this is a few things that are known. These are the few things that are known. What we are going to really talk about are degree 2 L functions. So far, so good? Yeah, okay. Okay. So let's recall what a holomorphic cusp form is. So what I'm going to take is that let F. So I'm going to abuse notation many times, but for now, let F be a holomorphic cusp form. And I'm going to do it for the group SL2Z, and I'm going to take a certain weight, K, bigger than or equal to 4. Okay. And very quick warm up of what a holomorphic cusp form is. So for this, recall the upper half plane. Right, so these are all the complex numbers that have imaginary part strictly positive. And that we have an action of SL2R on the upper half plane. So SL2R are all of these matrices ABCD with AD minus BC is equal to 1. And you have ABCD are real numbers. And this action is by what's known as Mobius transformations. And one can check that once you take Z to have imaginary part positive, the new thing is Z plus B over C, Z plus D also has imaginary part positive. So it's a well-defined action. And what we are interested in is in the action of a discrete subgroup on the upper half plane, and things that are functions that are almost invariant under this action. So what we have is also the fact that not just SL2R, but SL2, of course, then SL2Z acts on the upper half plane. Here you just end up taking the entries as integers. And what's a holomorphic cusp form? So F is called a holomorphic cusp form for SL2Z, exactly as I've written here, of weight K. I'm going to abbreviate weight as WT. So I mean, this is of weight K. If you have F of ABCD, Z, this is CZ plus D to the K of Z. Okay. So notice it's not exactly invariant. You have this extra factor that pops up. And then you have a few other conditions. F is holomorphic on the upper half plane, and at infinity that I'm not going to say anything more about, and that the Fourier coefficient, so F vanishes at infinity. But the main point of what I'm going to really do over here is that notice that you have the matrix 1101 in SLP. And if you take this matrix 1101 and act on it, take this and act on Z by it, you exactly get AZ plus B, so 1Z plus 1 over 0Z plus 1, which is Z plus 1. And if you look at the factor of CZ plus D over here, so CZ plus D is going to be 0Z plus 1, which is 1. So if you look at this particular condition, what that translates to is the fact that f of z plus 1 is equal to fz. That is, it is a one periodic function over the real line. And so you can Fourier expand this. So the Fourier expansion is, so this is also maybe partly something. The Fourier expansion is what you would have seen, maybe partly in Matstock. But let me just quickly say that again. You have, so F has a Fourier expansion. And the Fourier expansion is going to look like something that does not have the 0th term because it vanishes at infinity. And the coefficients look like this, where again, you're using the notation e to the 2 pi iz for ez. Okay. And one can associate an L series with this. Okay. One can first normalize the L function so that we write, so we can define, we can divide. So first we can show that the first coefficient does not vanish, make sure that it is equal to 1. So if you normalize it like this, what happens is that these actually match up with the eigenvalues of Hecke operators. Okay, so this is somehow a background. We are really not going to use this in any explicit manner. This is going to be a black box. But for completeness, I'm just telling you what is the object that we are actually working with. Right? So we also have Hecke operators for each n. And the good thing about the Hecker operators is that they satisfy, so the Hecker operators, if you act on it, let's say the eigenvalue is given by lambda fn. Okay. And the very nice thing about Hecker operators is that they satisfy this multiplicative relation. So if n and m are coprime, you have T and m is Tn, and then you act by Tm, or the opposite, right? And so that essentially gives you the multiplicativity of these eigenvalues. And it's actually not tough to show that if you normalize your Fourier coefficients appropriately, then those are exactly going to be the Hecke eigenvalues. Okay? And that shows you the multiplicativity of the Fourier coefficients. And once you have the multiplicativity of Fourier coefficients, you can expand out the L series, you can associate an L series, and you can write its Euler product. Okay. So we had, okay, it is that, but we have the Dirichlet characters, and Dirichlet characters are completely multiplicative. That allowed us to expand this thing, this L function, into an Euler product. We can actually do a very similar thing over here as well. So the associated L series we can first write as the Fourier coefficients over n to the s. It converges for real s bigger than 1 because you have the Riemann bound. So I've taken out its size right here. And so it does converge when real s is strictly bigger than 1. And because of the Hecker relations, you know that there is an Euler product. Okay. So what we need to know for this is that this is going to be a degree 2 polynomial in e to the negative s. Okay, it just turn out to be 1 minus lambda fp p to the negative s plus p to the negative 2s. But what is relevant for us is that it's a degree 2 polynomial. Okay. So we can also associate a conductor to the L function. The conductor, and let me be careful now. So the conductor in T aspect will be 1 plus T squared. Okay. By that, what I mean is that I fix my form F and I just let this parameter S, so I let this T go off to infinity by fixing the real part of S. And then I want to see what the rate of growth is. Okay. So the rate of growth will be again captured in terms of conductor. And the conductor is going to be, it's going to capture the degree of this L function. It's going to be 1 plus T squared. And the convexity bound now is going to be, again, the fourth root of the conductor. So the T aspect convexity bound is so okay, let me first write what this is. So it's conductor to the 1/4. So conductor to the 1/4 plus epsilon. And over here, I'm fixing my form F. So I will let possibly this implicit constant depend on the form and on this epsilon. And so the point is that this thing is going to be the square root. So t to the 1/2. So if you can get an exponent which is smaller than t to the 1/2, you get a subconvexity estimate in the T aspect. Good. So the first bound of this kind was actually by Anton Good in 1980. And he showed the bound of L1/2 plus IT F as 1 plus T to the 1/3, and 1/3 is less than 1/2. Right? So this was the first known convexity bound for degree 2 L functions. And then came along Tom Merman and Marty Utila. They proved it for mass forms. So I'm not really going to talk about mass forms. I'm just going to talk about this particular result, but we are going to prove it in a different way. Okay. So what we are going to do for this lecture and the next is to try and prove this via some delta method. Okay. And I'll try to give you the heuristics and also why the heuristics work the way they work. And this is like the main highlight that we have. Okay. So yes. Cannot go beyond what? Like the 1/3? Yeah, you can. I mean, for that matter, I mean, so the Lindelof hypothesis is also, I mean, if you believe the Riemann hypothesis for this L function, you also have the Lindelof hypothesis. So somehow conjecturally, the exponent should be just epsilon. Right. So the Lindelof hypothesis is also there, and entirely possible you will hear a talk that beats this bound. So, okay. Sorry, can you repeat, please? By Bougain. Yeah. No, so far I do not think that the known techniques get. Yes, okay. So you have an expert sitting with you. What's that? Bougain's bound. What's the exponent? 13/84. Yeah. So that's right. And it does not look like we can get to Bougain yet. Okay, does not think so. Okay. Okay, fair enough. So jury is still out on that question then. We don't know. Okay. Okay. So we have talked about, we have seen this Duke-Friedlander-Ibanez circle method or Duke-Friedlander-Ibanez delta method, and it's this avatar by Heath Brown that has been used. So let's also talk about a little bit about when it was first utilized by DFI and where it was used. Okay. So the first time it was actually used was in this Invenciones paper of DFI in 1993, where they were trying to prove a level aspect subconvexity bound. So you have this paper of DFI, if I remember correctly, it's called Bounds for Automorphic L Functions. This appeared in Invenciones in 1993. And this is the first time they wrote down their delta method. And again, a reminder, the way you can detect when an integer is 0 is to basically sum over all the divisors where w is a nice function. So this w satisfied some things. For example, w0 was 0, the sum over all the integers. So it had a good normalization. So you had all of these things. Right? And then you would go ahead and detect this condition, d divides n. So d divides n detected via orthogonality of characters. So you have 1 over q a, 1 over d a modulo d E, A, N over D. Right? So if D divides N, you get 1. If D does not divide N, you get 0. Right? This is exactly where the additive characters are coming inside the DFI delta symbol. And then, of course, you can massage this sum. You can write it in a better method. And we saw when I use it, and we saw Saurabh prove that particular version. Okay. So this was the basic idea, major idea going into here. And the problem that they were looking at was not a T aspect problem. The problem they were looking at was a level aspect problem. Okay. So let me also show you what that problem is, and then we'll take a break, right? So as you can associate an L function with a holomorphic cusp form like that, what you can also write down is a twisted L function. So what you can do is you can take chi b, let's take it to be a primitive Dirichlet character of modulus or of conductor Q. Okay. And then one can write down, so this is a twisted L function. One can write down this series like this. Again, converges for real is strictly bigger than 1. And then one can ask similar questions about the rate of growth of this L function. I mean, of course, one can also complete the L function. You can extend it to all of the complex plane. And you can ask how fast this L function grows on the critical line. Okay. So the problem that they were interested in is what happens if you fix your form and you let this conductor of Dirichlet character go to infinity. So DFI considered fix the holomorphic cusp form and let this Q go to infinity. Right? And over there is the first time that they used their delta symbol. Right? That's the genesis. So let me actually write down exactly what their result is so that I can state this. And, okay, so yeah. So the result that they had is L 1/2 plus IT F cross chi. This grows like T squared and Q to the 1/2 minus 1/22 plus epsilon. So notice that this is a polynomial bound in the T aspect. It's not a convexity bound in the T aspect, but it definitely is a subconvexity bound in this Q aspect, okay? Because the subconvexity bound in the T aspect is going to be T to the 1/2. This is worse, okay? So they just wanted to get a nice bound in the level aspect. So for simplicity, what we are going to do is we are going to consider the bound at, so I guess I should maybe write +1 over here. So let's consider the bound for or at t is equal to 0. And you can get this bound L1/2 F cross chi as minus 1/22. So how did they get this bound? They actually looked at a second moment average of these L functions. Okay. So what they did was that they considered a second moment average. Okay. And the philosophy is somehow very nice, and a lot of proofs use that if you can sum up positive things and get a bound for all of those, then the bound holds for each of those things. So the bound, the kind of the kind of object that they were considering was something like this. And let's say we can prove this particular bound. Now you're summing up a bunch of positive numbers. So this whole bound is going to be true for each of these. Okay, so this is going to imply that L 1/2 f cross chi squared is less than b. And in particular, if you take the square root, you get the bound of b to the 1/2. So if you're able to prove a bound for a moment average of L functions, you can also get a bound for a single L function. Okay. So they considered a bound like this and got a bound like this. So I want to show you a bit of calculations, the starting of calculations for Dietrich-Landry and Ibanez's paper. So they have a second moment average. And the first thing that they do is use an approximate functional equation. So as Matt had shown us yesterday, you can write down an approximate functional equation. And this is going to be a sum over all of these n's. So you have lambda fn by n over n to the 1/2. And then there is going to be a certain function plus there is going to be a root number. In this case, it's not dependent on chi, actually. And you get this. And you have it. And this function v is basically going to capture what the size of this n is. So how far do you have to sum up these n in order to capture this central value? And it's sufficient to sum it up to q to the 1 plus epsilon. And this is a general philosophy, actually. Again, let me remind you that the conductor in the level aspect is the conductor of chi raised to the degree of the L function. And the length is going to be the square root. So this is length is the square root of this conductor. Okay. So I can also write that this is less than q to the 1 plus epsilon. And as I had promised, the convexity bound falls out of here. So for now, if you let me assume the fact that so you have Dahleen's bound on all of these Fourier coefficients. You don't quite need it, but for simplicity, let's assume that just trivially bound all of these things. So we know that this is some complex number with absolute value equal to 1. And if you put the absolute values all the way inside, we know that chi n's also have absolute values once. We know that lambda fn have absolute value, big O of n to the epsilon out of caution. And you can do the same thing over here. And so the bound that you get from here is going to be n going up to q to the 1 plus epsilon of n to the epsilon n to the 1/2, which is q to the 1 plus, q to the 1/2 plus epsilon. And over here, each epsilon is possibly different. Right? It's an arbitrary constant that can be like small. Right? And that is exactly your convexity bound. Just a second. Could you repeat, please? So V is, and all I'm going to write here is that it's a well-behaved function. But what it is something which is supported in 0, 1, and that and what you can also do is that you have some very nice bounds for this thing. So you have something like this. Say again, please. What's the length? So it's supported in 0, 1. So essentially, it means that n is only going to be going up to q to the 1 plus epsilon. Right. What you can also do is you can then start looking at only one of these factors because they look similar. If it's an SL2, if it's a holomorphic cusp-form for SL2, then we also know it is self-dual, so this is going to be actually real. And what you have over here then is sufficient to consider only one of these. Sufficient to just consider, let's say, summation and going up to this length, and you have lambda fn pi n over n to the 1/2. And now I'm going to commit the first, I guess, so the first abuse of notation is going to be that I'm going to drop writing the weight functions. Okay? So I'm not going to write the weight functions, but everywhere there will be smooth weight functions that have very nice bounds. So you should remember that it is, but if I'm not writing it, it does not mean that it's not there. It's not a sharp cutoff. Okay? And the second thing you can do here is that as you saw in the previous lecture for looking at the S3 sum, you had dyadic partitions. So what you can do is over here, you can partition n going from 1 to 2, then 2 to 4, then 4 to 8, right? Something like this. 2 to the j to 2 to the j plus 1. So in the middle, there is a segment that goes from some big N to 2n, right? And what one should also observe is that there are log q many of these. So by using a partition of unity, you can again multiply by that, and you can consider not the full Dirichlet polynomial going from 1 up to q to the 1 plus epsilon, but only going in dyadic segments. So you can bound that particular thing. Sure, yeah. Over here, I did use Ramanujan-Peterson conjecture, which is known for holomorphic cusp-forms, but you don't necessarily need it. You can use Cauchy-Schwarz inequality actually, and you use Rankin-Selberg on average. But you can basically get the convexity bound out of that if you know Rankin-Selberg bounds, for example. Okay, so if you write the whole thing over there, what you can actually get here is there's a log factor that we don't quite care about because we want exponent savings, and then supremum over all of these n's going to q to the 1 plus epsilon. And this particular sum, which is lambda f n pi n over n to the 1/2. And again, when I'm writing this particular notation, I mean that there is a smooth bump function that makes sure that the small n is in between these things. Okay, so there is a smooth bump function. It's not a sharp cutoff. Good. And also what you can do is you can multiply and divide by big N to the 1/2 like this. Let me take out one of these big N to the 1/2 outside, and let's combine this small n with big N. So you have big N over small n to the 1/2 right here. Now, if small n is between big N and 2n, then big N over small n is only going to be between 1.5. So you can also absorb it in the weight function, right? So let's also absorb this in the weight function. And so essentially what you are left with is considering this particular object, which looks like this. Okay, so we're going to try and bound this object. If you can bound this, you can bound the L function. Okay. So what DFI did was look at a second moment average of this particular thing. And I just want to say a few words here because I want to show you that it leads to a shifted sum problem. So let me not erase the result. Let's also keep this. So what they did was they considered, can I repeat this? Oh, so if you can get a bound for this, Sn, right, then all you have to do is divide by square root n and take the supremum over all of these big n's going over here. Oh, so this capital N over small n is some number that goes between 1 and 1/2, because small n is going to be in between big N and 2n. And so you can absorb this in the weight function. So let's say that the weight function is like x times your original weight function. Right? So this is absorbed over there. And it's not going to change the properties. The derivatives are still going to behave nicely. Right? So that's why I'm just getting rid of it, just so that you have a cleaner object. So you just have things that depend on the Fourier coefficients, the Dirichlet characters, and this is essentially a constant for us. So what they did was they considered this particular second moment. So they considered second moment of this Sn. So let's write this lambda Fn chi n. And again, if you're able to get a bound for this, then you can drop all the other terms, just get one of these, and then the bound that you get for one of these is square root of b1. Then you divide by square root of big N, and that gives you a bound for the L function. One thing to note here is that I'm summing over all the primitive chi's and not all of those, because once you write down the approximate functional equation, where you cut off depends on the conductor of chi, right? So if chi is not primitive, where you cut off is going to be a smaller length, okay? So that's going to be a little problematic, but there is a very nice way, a nice trick to get over just chi being primitive. You can use the Gauss sums and the inversion because of it, and you can complete it. So I'm not going to go over exactly how they did that. It's maybe a two-line argument, but let's open this up and see what you get. So if you open this up and write things down, and maybe let's also divide by the number of things that there are, what you get over here is that this is now going to be, if you open the absolute value squared, it's going to be a double sum. Let's say n1 and n2, and you have lambda f n1, lambda f n2, and you have this, and then you have this, and you have pi n1 chi bar n2. I did not exactly justify why you can do this, but you can actually get rid of the primitivity condition, and you can multiply and divide by the number of factors that there are. And then this particular condition gives you exactly that n1 is congruent to n2 modulo q. Okay. And now let's change variables again. Let's write n1 as n2 plus h. But one of the things one should notice is that the sizes of n1 and n2 themselves are only going to go up to q to the 1 plus epsilon. Okay. So if you take this big N to be anything which is smaller than q, then this is an actual equality, and it doesn't give you anything more. So you have to do a little something more in order to actually extract cancellations. The little something more that they do is a method of amplification. We are not going to see that in the two lectures, but what they do is that they multiply by a certain factor. So this method of an amplifier was first used by Ivanic. They use this particular extra factor, and then they open the absolute value squared. And once you do that, these shifts are not going to be trivial. So a priori, it looks like that H is going to be less than the size n over q, which is trivial if n is strictly less than q, but you can essentially get over it. The point is that once you have all of this, you can write this double sum as lambda f n1, lambda f n2 bar, and then you have to write n1 is equal to n2 plus h. And this is exactly the condition where DFI use their delta symbol. So in order to detect a shifted convolution sum, they used their delta symbol. Okay, so you can of course write this n2 as n1 plus h, if you will, and you see that it's a shifted sum. That is, you're not multiplying. So the two coefficients that you're multiplying are not at the same index. It's a shifted index. Okay, and they looked at the shifted convolution sum problem, and they were able to get certain cancellations and get the result. Okay, but we are not going to do that. What we are going to do is we are going to directly apply a delta symbol right here. And this was, as far as I understand, some such philosophy was first utilized by Ritabrata Munshi. So what he was looking at were some GL3L functions and their twists. And he said, all right, why not let's look at this particular object and write this thing as a double sum right away. Let's say n and m of size n and lambda fn by n, and detect n is equal to n. So this is not a moment method, right? You're not taking moments of L functions. It's not a shifted sum problem. You're directly detecting, as Saurabh had also explained in one of the previous lectures. We are just going to apply the delta symbol right here. Okay. So the rest of this thing and the next lecture is going to be about proving a wild-type subconvex bound for degree 2L functions, just for holomorphic S forms. Okay. Sorry? In the T aspect, thank you. In the T aspect. Specifically, we are not going to look at the level aspect. We are going to look at the T aspect result. Okay. So before we change gears a little bit, do you have any questions or comments? Yes. How do I take care of what thing? In primitive characters. Oh. So I have to remind myself before writing it down. So the first thing you can do is you can write a Gauss sum, tau chi as summation of chi a times e a over n, e a over q, and then you can write basically chi bar in terms of a summation of additive characters multiplied by or divided by a certain Gauss sum. Once you have additive characters, you can complete that particular sum. So basically the fact that Gauss sum is 0 for imprimitive characters. And then, say again. Okay, okay, fair enough, yeah. Okay, okay, yeah. So yeah, you have basically ways to go about this. Yeah. Yes, that's right. Yes, for orthogonality, you do need all the characters. You're right. No, 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 I'm not doing that. Over here, you see that I'm not having any condition on primitivity versus imprimitivity, right? over here as well, what you can do before actually opening the absolute value squared, or rather maybe, yeah, before opening the absolute value squared, you can write, okay, let me try and remind myself. So this is tau chi chi a e a over q, where you have a modulo q. So let me write this over here like this. And then let's take n and q to be co-prime so that you have something like this. You have this, and this is multiplicative. So this comes out, and you have pi bar n. So what you have over here is that write chi of n as 1 over tau chi bar, and then a summation of a modulo q chi bar a e a n over q. So you start with writing your chi n like this, right here. Okay. Then the next thing that you do is that these a modulo q are going to detect certain orthogonality relation. So you are passing from multiplicative characters to additive characters. Once you have those orthogonality relations, you add up the rest of the classes. And then you do it again, do it back. And you basically are then able to get all the classes. So this is basically what you can use and get to. Yeah? Okay. Anything else? Okay. So let's make a few comments about the delta symbol, because of course, we should be able to choose a nice delta symbol in order to make things work. Okay, let's get rid of. Things. So we have this so-called trivial delta symbol. Let's say you want to detect how when n is equal to 0. What you can do is you can detect when n is congruent to 0 modulo q for this parameter q if it is strictly bigger than absolute value of n, right? What you can also do, for example, is let's say if you want to detect when two things are equal to each other, you want to detect when their difference is equal to 0. Let's say to begin with that these two parameters are something that lie in a dyadic interval. Okay. What we're going to do is we can say that this is the same as saying that n is congruent to r modulo q, and you have an extra imposition that the distance between these two things is going to be, let's say, less than a certain parameter x if you're able to choose this parameter q to be strictly bigger than x. Okay. Of course, in practice, it will make sense to choose your big X to be something which is less than the trivial distance between these two numbers. I guess I can just take it to be n. So in practice, we would like to choose X to be strictly less than n, actually less than some power of n. Okay. And this is, both of these are in literature what we have been calling a trivial delta symbol. And we're going to utilize this particular, the second one, in order to prove a t aspect while bound for this GL2L functions. And let's detect n is congruent to r mod q. So you can do that by additive characters. So you have a modulo q sum. right? You have right E A n minus R over Q. And yesterday we had this discussion about an integral, or so basically an integral to show this particular condition. So we want n minus R in absolute value to be less than x. So what you can do is you can write E n minus R small x over big X, W small x dx, where you have that the integral of W is 1, and you have all of these nice bounds on it. And let's say W is supported in something like 1 to 2. Okay. Why is this true? All you have to do is integration by parts. So you should differentiate this factor, and you should integrate this factor. If you differentiate the weight functions, you will get its derivatives. And if you integrate this particular thing, then you will get the reciprocals of all of these. Right? So if you do integration by parts, all of this is going to be bounded by powers of the reciprocal and times this. So if n minus r is too big, let's say it is bigger than x to the 1 plus epsilon, then you end up getting negative powers of x right here. So that this is going to be arbitrarily small. Okay. So it just means that n minus r has to be less than x and some power. So maybe I should be a little careful. I should write x to the 1 plus epsilon. It can be any factor that grows polynomially, actually, and you have this. So if one can make sure, so just to be a little more careful, maybe I can write 1 plus epsilon right here and make sure that q is bigger than x to the 1 plus epsilon. We have a delta symbol right here. Okay. So we have this trivial delta symbol. And I also want to make a comment about the Klusterman version of delta method that we have seen. And that kind of relates with all of these delta symbols. So a reminder, what was the Klusterman's? I'm not going to write what the Klusterman delta method or circle method looks like, but the point was that you start with an integral like so, and then you divide this arc, right? How do you divide this arc? Well, you have 0 to 1. You look at all the fractions, a over q. So these are all the reduced fractions. These are the Fourier fractions. Such that a is going to be less than q and coprime. And you have these denominators going up to a certain size. So you take all the Fourier fractions, and then you divide up your whole circle, whole arc. How do we divide up this arc? We have to be careful about dividing up. Essentially, we divide up this arc so that Dirichlet's approximation is true, right? So we divide up this arc like this. So if there are 3 adjacent fractions, so in this Fourier sequence of depth q, if these are 3 adjacent things, then the way you do it, the way you make an arc around a over q is by finding the medians. So the median right here will look like a plus a double prime over q plus q double prime. And the median right here is a plus a prime over q plus q prime. The good thing is that what that does for us is that it divides this particular interval in exactly the ratio q prime is to q. Okay, so that's how you're dividing it up. But no one is telling us to take all the fractions in the Fourier sequence. You can take as many or as few as you like. So let's not take all the fractions in the Fourier sequence. Okay, let's fix a prime p. Or let's fix a denominator q and take all the reduced fractions modulo q. So you have a new thing. You have a subset. Let's call it S sub q of these Fourier fractions. And this is a very silly thing. It's just A over Q, where you have all of these. And maybe let me take it to be prime. Let's take it to be prime. Okay. Let's do this. Okay, along with 0. And do the same idea and see what you get. So if you do the same idea, oops, I didn't want to erase this. Anyway, so if you do the same idea, what you have over here is A over P. Over here, you have A minus 1 over P. Over here, you have A plus 1 over P. You can write down the medians. And this is going to be exactly, so the point was that if you write down the medians, it's exactly going to divide it in this particular fashion, in this ratio. So since the denominators are the same, it's only going to divide it as 1:1. So what you're doing is that you're taking just a uniform partition of circle. Right? So this is basically going to be, so all of these, each of these are arcs that are going to be of length 1 over p. And what you have done now is that this gives you a uniform partition of circle. And you can write down a circle method like that, right? So let's do that and see what you get. So if you write down the circle method by uniformly partitioning the circle, you get this integral 0, 1, e nx dx. But what we are saying is let's partition this thing. But here now the fractions are going from a over p to a plus 1 over p. Right? And now do a change of variables. So do a change of variables. Let's do 2 change of variables together. Let's go take x going to x plus a over p. And then let's do the next change of variable as x going to x over p. So if you do these change of variables together, you will end up getting this expression, which is 1 over p summation a modulo p e a n over p integral 0 to 1 e nx over p dx. So you have this. And now you see that this looks awfully similar to your trivial delta method, right? This is exactly what's capturing the congruence condition, and this is kind of what is capturing that something has to be small. So here, because you don't have the weight function, you cannot exactly say that absolute n is less than p. But if you were to smooth it out, this is exactly what it says. So the trivial delta method is akin to taking a uniform partition of circle and working with that. Okay? Because it's a sharp integral, it's not the best to work with. Later on, when we do stationary phase analysis, it's not the best thing. So we are going to work with this particular delta symbol, and we are going to apply it to the L function and try to prove a subconvexity bound for that. So maybe I'll pause for a few seconds if you have any questions or comments. Right, right. You can take anything. For example, you can take, I was just talking to someone, right? So you can, for example, take a subset where fixed prime does not divide Q, or you can take the subset where all of these denominators are square free. I don't know. It depends on your problem. Also writing it down. So, I mean, if you have, for example, if you can write down this thing for other subsets, I'll be very interested to see that. Maybe there are some nice applications. I mean, at least for some subsets, I do have some nice applications in mind. So yeah, we can talk more. Right? Yeah, fixed prime. I mean, of course, you have to let the size go to infinity depending on the problem at hand. It's a parameter. Okay. So in the last 5 minutes, all I want to do is quickly set up the problem so that the next time we can start with the application. Yes. Yeah, so it should be 1, but here, I guess, let me take strictly less than this, and I'm also taking the Fourier fraction at 0. So 0 is 0 over 1. That's the fraction I'm taking. So I'm also taking 0 and 1 always, and then all the fractions in between these. It does not include, it's a subset of it. Yes. These are all the reduced fractions. Okay, I guess I just want to write down the setup of the problem so that the next time we can take it up from there. And what we will be looking at is the L function. So without really saying many words, I'm just going to do the same thing as we had done for the DFI. So the difference is that in Dupre-Nader-Ivanich, we had chi n. Over here, you have 1 over n to the I. Right? And so if you can bound these particular things, let me call this Sn. So if you can bound these nicely, then you have your result. Okay. And what we are going to then do is essentially look at this Sn and write this as a double sum. No, over here, I'm not looking at the characters. Here, I'm just looking at the L function of a holomorphic form. So, I mean, I do have the Archimedean character, if you will. Don't have any non-Archimedean parts, right? And we are going to use the delta symbol that is written right here. And then we are going to basically do the analysis and try to show a good bound. A second thing that we are going to do is that we are going to do things in the sketch form. So notice that this particular bound that we are trying to prove has to work for every big N. So in particular, it has to work for the biggest of the N's. So in the sketch form, what we are going to do is we are going to take this big N to be T. For smaller N's, a similar analysis will go through, and we are going to prove a certain bound. Of course, if this big N is too small, then the analysis cannot go through. So what we are going to essentially do, therefore, is that we are going to break this into two segments when N is going up to, is at least a size n to the delta, and it's going up to the size n to the delta. Over here, what we are going to do is we are going to use the trivial bound. And over here is where we are going to do our analysis. So we have to be also careful about what we choose this delta to be. And that will basically come up in the calculations in the sketch that we show. Okay. Okay, good. So it's time for lunch. So the next time we are going to look at these things and we are going to apply the delta method, the trivial delta method.
Thank you very much. Are there any questions? Okay, it does not look like. No. Yeah, then let's thank the speaker again.